parched right now, but I don't know where my guide dog is, and I forgot where I placed my water bottle. How can I find my water bottle right now? I do not know where to go. I think I remember putting my water bottle this way, but I'm not sure if there was anything in the way. Let me try to get to it. Oof, there's something in the way. Let me try to go this way. Oh shoot, I think I ran into a dead end. What am I going to do?
Hey, are you looking for your water bottle right now? I think I saw it. I could maybe help you guide.
Yes, that'd be great. Could you tell me where to go?
Yeah, of course. I can do that for you. Let's get started. All right, let's do it. So all you have to do is go straight.
Go straight?
And then left.
Oh,
and
no,
right. No, left again.
Left
Your
again?
left, my right.
Man, I'm not sure where I'm going. I wish there was a better way to do this.
Maybe? Yikes, that was horrible. Perhaps there's a better way we can do this. Let me go hit up my buddy and maybe see what we come up with. Okay, so what you saw there, that was a problem. And that was the motivation for our project. So we initially wanted something audio related, but we also wanted something beneficial to the general public. All right, so to get a little bit more in depth, let's go over our motivation for this project. Sound is primitive. Sound already carries spatial information that we use in our daily lives. We already use sound in our day-to-day lives to hear where things are and to navigate our lives. But now the question is, can we engineer that into a reliable guidance system? Our bet is yes. Why not use a guide dog, you might be thinking right now? Well, the problem is a guide dog might not always be able to help you in an indoor, unfamiliar environment. Especially if you're trying to find objects inside the building, like the person over there that I was trying to help.
I still do not know where my water bottle is. I wish I could find it.
And this is why we came up with Pathsong.
Let's go into the background of Pathsong. So what exactly is Pathsong? Pathsong is sonified navigation for visually impaired users. We stitch together object detection models, navigation models, to output audio that is digestible for users. We'll get into how exactly that works now. For our main tools, we use the yellow object detection model, which helps us identify objects, as well as the A-star pathfinding algorithm, which generates an optimal path for navigation. So, as we were discussing in our motivation, when we were thinking about what type of audio parameter to use and how we would communicate to the user which direction to move and where to go, we realized that speech was kind of bad because speech is very intrusive and oftentimes it can overwhelm our users and they end up not knowing exactly what to do and it comes at them too fast. So this is what we decided on for our audio parameters. There'll be 3 distinct sounds that come at you to tell you what direction to move in. So first is our bearing, and bearing is like how far you are from the direction you're supposed to be moving in, and this sound came at you in a low wub. So imagine you're moving this way, and if you're very far away, the sound would be pretty loud and it would be slow vibrational noise that plays in the background, either in your left ear or right ear based on spatial audio, and as you turn to the direction, the sound gets quieter and quieter. Once you get close enough, there's a directional chirp, and this chirp tells you that you are pointing in the right direction and you're good to go to move forward. And finally, depending on if there's objects in the way or if you reach your final destination, once you do, there's a successful chime that tells you, yes, we have arrived, and now the user can look for whatever object that should be in front of them.
One go.
While we were testing, we realized that we probably needed 2 more sounds. First one was for obstacle detection. And this, again, was just a low wub and a different frequency that told you, hey, you're coming close to an obstacle, and then the bearing wub and the directional chirp would come in to tell you to turn in another way to reach your destination. And second, realized that when we were scanning for initial object in our environments, we needed a sound to play that told the user that they were scanning before they were given the go to start moving towards their object. I already talked about our simulations a little bit when I was talking about the audio, so let me go a little more into detail. So we used 2 simulations. First was Pygame, and this was a 2D sim, and this was mainly to test and fine-tune our audio parameters. And so we tested our parameters based on different frequencies, timings, to see what audio our users responded best to. Second, we also had AI2 Thor, and this was a 3D simulation environment that we, number one, used not only to train YOLO on for object detection, but also number two, this was our final 3D simulation environment that we used Pathsong on to navigate and find objects for in our demo. For Pathsong, we had to fine tune and train a couple of these models. So for YOLO specifically, YOLO is actually trained on real life objects and the labels associated with those real life objects. And so in our AI2 Thor simulations, these objects might look the same to us, but to this model, these objects look completely different. It can't tell a pot in the real world versus a pot in the simulation. And so AI2 Thor actually very conveniently gives us a list of these objects with ground truth labels. And so we train YOLO using transfer learning so that it could understand what these objects were in AI2 Thor's simulation environment. We also use Gaussian process regression on the data we got from the trials we ran in our Pygame 2D simulation. And these regressions were used to help optimize the audio parameters for our users. And so this helped us tune the frequency and the timing that best suited our users' needs.
Okay, moving on to how it works. So the way our model works is that it first takes a query from the user. In a final implementation, this would probably be using speech to text so that users could query objects just by speaking. But currently this is just passed in as a text argument for simplicity and to ensure that everything is mapped correctly to YOLO classes. Once this query is passed into YOLO, YOLO scans the current frame to see if the object is detected. This version of YOLO has been fine-tuned using objects from AI2 Thor. Once YOLO locates the object, it uses AI2 Thor's depth map and coordinate map to find the exact location of that object. In real life, we could replace this with a Midas layer, which would do monocular depth estimation from the camera itself. But for simplicity, we opted to just use the existing floor maps. Once we have that desired coordinate, that's passed into A star. A star is a pathfinding algorithm that determines the optimal route from the current user's position to their desired position. Our version of A star has been modified to prioritize straight line directions. So rather than having users follow curved paths, it prioritizes them moving straight as long as possible. Finally, once these directions have been created using A star, they're sent to our final audio mapping, which was developed using the Gaussian process regression. And this audio mapping conveys to users how to reach their desired object. All right, now for a quick demo of the simulation environment we used to generate the audio parameters. So as you can see, it's a 2D plane with various obstacles, and your optimal path is computed as you move along it. So in the bottom right, you can see audio. Right now it's currently pulsing. Pulsing means move forward. And as you have a larger and larger bearing error, you're told to stop and correct it. So as I move along this, you can see that bearing left needs correction. This would actually be audio playing in the user's headphones, telling them to turn left. And once their bearing is correct again, they hear the pulse. And now just for a quick look at the accuracy per class of our fine-tuning, you can see that it's not very high. This is primarily because generating a data set using Thor was very computationally expensive. It took 2 days just to generate about 3,000 images, or sorry, 3,000 images. And so our data set was rather limited, but you can see these are all classes that are unique to Thor that were not present in YOLO before, that it's been fine-tuned on. And I mean, all the accuracies are reasonable and above our minimum confidence, so it actually does work in practice.
All right, so now we're going to showcase a live run through the entire pipeline working end to end. So right now the navigator is rotating across the entire scene. This is the YOLO model trying to initially locate the microwave to start the pathfinding. And we'll see it scanning the entire scene right now. And once we see the YOLO detection actually find the target, which would be the microwave, we can see the pathfinding doing its job, so navigating around all the obstacles, working real time to adjust based off where the person currently is in the scene. And the audio instructions are being visually overlaid through the little box on the bottom right corner, showing whether we need to change our bearing a certain amount of degrees or move forward. And once we've reached the arrival threshold of a certain distance and bearing within the arrival target, which it is about to get to right now, then it shows as arrived. And that's the entire pipeline.
And finally, for future improvements and shortcuts that we took. So in terms of future improvements, the main two would be getting it ready for real deployment. So first, that would be implementing a speech-to-text model. This means that users wearing a headset could query the model and tell it, okay, get me to object A, and that would naturally be converted into a YOLO query, which then routes you. The second improvement that we thought of was integrating a multimodal LLM. What this could do is look at a picture of the scene and provide a semantic description of the directions that the user is about to receive. This could help them get a sense of what's actually going on while not overwhelming them with audio. In terms of shortcuts, the main one was using ground truth from AI2 Thor, our 3D sim. We used its floor plans and its true depth map instead of computing those using some kind of depth estimating model. This does exist and is used in practice. Most famously is MIDAS, which is a monocular depth estimator. But we figured that it was not really relevant to the scope of our project and would just complicate things. We hope you enjoyed our video. We really enjoyed sharing our project with you. Thank you so much for watching this video. Have a great summer break.